We're exploring the dazzling new images from the Vera C. Rubin Observatory this week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. Today, we explore the first public release of images from the Vera Rubin Observatory and learn more about the powerful telescope behind them. Stephanie Deppe, a planetary scientist and astronomy content strategist at Rubin Observatory, joins us to explain how this revolutionary facility works, what these first images reveal, and how Rubin will transform our understanding of the universe over the next decade. Later in the show, we celebrate the observatory's namesake, Vera Rubin. Jess Soto, who's the STEM Strategies Coordinator at Mount Wilson Observatory and founder of Science Women Shirts, shares how Rubin's scientific brilliance and advocacy for women in science continue to shape and inspire future generations. And of course, we'll wrap things up with What's Up with our chief scientist, Bruce Betts, with a discussion of the third interstellar object ever discovered, Comet 3I Atlas. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. On June 23, 2025, the Vera C. Rubin Observatory released its first public images, offering a dazzling glimpse of the universe captured at an unprecedented scale. In just over 10 hours of test observations, the telescope imaged millions of galaxies and stars and discovered over 2,100 never-before-seen asteroids. These are the very first images shared with the public, but behind the scenes, Rubin's team has been hard at work for months, gradually bringing this next-generation observatory into focus, fine-tuning the systems, and preparing for its official science mission. Perched high in Chile's Cerro Pachón, the Rubin Observatory is the product of more than 2 decades of vision and engineering, jointly funded by the U.S. National Science Foundation and the Department of Energy's Office of Science. Its state-of-the-art 8.4-meter telescope and record-breaking digital camera, which is the largest humanity has ever built, will capture a dynamic time-lapse record of the universe over a 10-year mission called the Legacy Survey of Space and Time. That survey is expected to reveal everything from dark matter and dark energy to asteroids, interstellar objects, and cosmic events that we haven't even imagined yet. The release of these first images was a global event for space fans. More than 300 institutions, schools, and science centers around the world hosted watch parties for the image release. And Rubin isn't just for scientists. With new tools like their Sky Viewer and a dedicated public engagement platform, the observatory is bringing astronomical data on an unbelievable scale into classrooms, homes, and citizen science projects, making real exploration of the cosmos accessible to anyone with an internet connection. The observatory is named for Vera Rubin, the legendary astronomer who found the first convincing evidence of dark matter. We'll learn more about her story and her legacy later in the show. But first, to talk about this historic image release and what's to come, I'm joined by Dr. Stephanie Deppe, astronomy content strategist for Rubin Observatory. Stephanie is a planetary scientist, astronomer, and science communicator, and she's one of the voices that are helping connect this remarkable observatory with the world. Thanks for joining me, Stephanie.
Thanks for having me. I'm super excited to talk with you.
Well, this is a moment that's decades in the making. Building an observatory of this size takes so much love and so much effort and so much international collaboration. What was it like for you after all of that to finally get to see these images for the first time?
It is so hard to put into words. I have seen kind of the end of all of this planning and the lead up and the excitement from everybody who has been involved for decades. Just getting so excited about the imminent release of these images and the turning on of the observatory. Yeah, the first time I saw the images, it was a really surreal experience. There are a number of times I've seen kind of first images, I guess. The first one was when we turned the commissioning camera on for the first time. And this is a smaller engineering test camera. And that was the first time that photons had ever come from space, bounced through the telescope's mirror and hit a camera detector. And so that was like a really special moment that happened back in October of 2024. But the next kind of moment that all of this kind of felt like it was leading up to, and it's kind of like the moment that everyone who has been working on Rubin for 20 plus years has been waiting for was what we call first photon. And it is the moment when the LSST camera, the big car-sized camera, was turned on, pointed at the sky for the first time. That moment was a party. like we kind of were narrowing in on the day it was going to be, but like up until probably the week before, we didn't know exactly what day it was going to be, because it just, takes time to get everything into place and check all the boxes and whatever. And you're assembling this huge facility, this telescope, this camera, like you're putting all of these components together for the first time. And so you don't know how it's going to work until you plug things in and try to turn them on. And so finally, like kind of a few days beforehand, we were like, okay, we're pretty sure it's going to happen on April 15th. There was kind of like this buzz around like all of the meetings that I was in, because everyone knew that like it's happening tonight. Like we are turning this giant camera on, and there will be stars and galaxies visible like in this camera for the first time tonight. And so they kind of last minute scrambled to put together a kind of staff-wide Zoom room. So there were a bunch of people who were on site, but most people who work for Rubin are not in Chile. They're in the US or they're elsewhere. Yeah, there were probably 200 people on this Zoom room, plus probably another 100 people who were throughout the various control rooms, like in person gathered. And we got the announcement like, okay, the shutter's open, we're taking the image. And then like, okay, shutter is closed. And we were all just like, where's the image? And then on Zoom, everyone like in the control room who was like actually physically there just started cheering. And we were like, we can't see anything.
What's happening?
So everyone on Zoom was like, we can't see anything, but we know they can see something. And so it was probably another 7 seconds. It was the longest 7 seconds ever between that first cheer. We knew that first image was on the screen in the control room, and when the rest of us online were able to see it. And then, of course, that first image was not in focus. Like it's not going to be in focus the first time you put everything together and turn it on. Like it's just not. It was pretty close though. Like it was amazingly close, because the observatory, the telescope has like laser trackers that help align everything without having to take an image, but it's not like exactly perfect. And so they took this image and it was out of focus and everyone was all excited, like cheering. And then they were like, okay, now we have to work. We have to get it in focus. And so they started taking like successive images. And this camera is amazing because it is 3,200 megapixels, which is a lot of pixels, and it reads out those 3,200 megapixels in 2 seconds. It is incredibly fast. And so they started doing kind of like these iterations to bring the telescope into focus and bring the images into focus. And you take like a 30-second exposure, wait 2 seconds, and you're like, okay, it makes it. So like, it's really fast to do this sort of iteration. And within 3 or 4 minutes, it was in focus, which is amazing.
Well, this release was full of these just absolutely mind-blowing images. I cannot imagine what it would be like to be on the team after so much time working and then finally see these. They're I don't have words to describe what these are like. So I'm going to post them on the episode page for this episode so people can look at them themselves. But all of that was accomplished in like 10 hours of test observations. How does that compare to what we're going to be seeing when this thing is in full operation?
Yeah, so I will say that the way that these first look observations, these first images, the way these observations were taken were a little bit different, just in the sense that like the goal was to create these beautiful images. And so we were very much focused on these 2 patches of sky, the M Messier 49 Virgo cluster region and the Trifid Lagoon Nebula region. And so the way that those observations were captured is not exactly the same as how the observatory will operate in normal kind of science operations, but it also kind of was. So we have something that's called a feature-based scheduler, which is a software algorithm that determines where to point the telescope next in the sky. And this is to really optimize the shutter time that's open, the time that we have the camera actually on sky. The software will map out the most efficient pattern to map out the sky based on, where we've already covered, where clouds are in the sky, where the moon is, like all of these different factors. They'll take all that in and be like, okay, the next best place to point is here, go here. And so that software was what drove these observations, but it was restricted to like these specific areas rather than the whole sky. So that kind of mechanism for taking the observations was very similar to how Rubin Observatory will operate, but it was just restricted to these two smaller portions of sky. So ultimately what we got in these 10 hours for these two patches of sky, was particularly for the Messier 49 Virgo cluster region, it's comparable to about 5 years of the full 10-year survey is the depth that you're seeing there. So we're going to get more. It's going to get even better, but that is kind of what you can expect from year 5 out of 10 of the whole survey.
What exactly is this survey going to be trying to accomplish, the survey of space and time?
It's going to try to do everything, which is always a very ambitious thing to try to do. But the whole point of Rubin is really to see everything. It's going to take these all-purpose images of the sky. It's just going to look for the sake of looking. It's going to record what it sees and send that to our supercomputing data centers. And then the scientists will come in and sort through that data and filter it and, curate the set of data that they need just for their specific area of science. And so the way I've heard it described, and I've kind of started describing it, is Rubin is not giving data to scientists. They are bringing scientists to the data. It's a very fundamentally different way of doing astronomy. Like scientists are not going to be downloading this data to their laptops. I mean, they might, but we're talking like 20 terabytes of data every single night. You just cannot download that to a laptop. So everything's going to happen on supercomputers in the cloud. So Rubin will get really precise data on galaxies and galaxy clusters, very distant galaxies. This will help us understand more about dark matter and dark energy, how the universe is expanding, how it clumps due to gravitational effects of everything that's in it, and how those two kind of play together to shape the overall large-scale structure of the universe. Because Rubin is going to see everything, it's also going to see a whole bunch of stars in our Milky Way. So Rubin is going to create the most comprehensive and precise map of the Milky Way ever generated. We're going to see more stars than any previous observatory has been able to map in the Milky Way, which will help us understand the evolution and structure and history of our own galaxy. The part that I'm personally most excited about, I'm a solar system astronomer by training. Rubin is going to create the most kind of comprehensive inventory of the solar system that's ever been generated. Currently, we know of about 1.5-ish million asteroids in the solar system, and Rubin is expected to discover up to another about 4 million than what we currently know. And so that's going to give us a lot of information about what's in our solar system, how did it get there, how did we get here, and just generally the evolution and history of our solar system. And then finally, the fourth kind of primary science driver of Rubin Observatory is looking out into the universe and seeing what changes, the changing, dynamic, transient sky. So the way that the Legacy Survey of Space and Time operates is we get a new snapshot of the entire Southern Hemisphere sky every few nights, about twice a week. And with that, you can essentially play a game of spot the difference every 3 to 4 nights. You look at the sky, and the next time you visit, you see what changed. And the next time you visit, you see what changed again. Rubin is going to be doing this over and over and over every night, and essentially alerting the entire world about all of the changes it detects every night.
Just to give people an understanding of the camera on this thing, in last week's show, we talked a little bit about the physical size of this camera. It's like the size of a car. It's like huge. But this is the biggest digital camera ever built in the history of humankind. What makes this camera so special?
There are a few things that make it pretty special. We actually have a couple of Guinness World Records for different parts of the camera. We're in the Guinness Book of World Records for the largest lens ever made, which is, literally human sized. It's about, I think, 5 feet tall, which is, maybe relatively short human, but
it's like me size.
I know, it's huge. It's giant. And the other really special thing about it is its focal plane, or that kind of grid of CCD detectors. There are 189 of them that are used for science. And then there are a few that are used for like helping to focus and these other kind of fine-tune adjustments to make the image quality as good as it possibly can be. That focal plane, I believe, is also the largest focal plane ever constructed. And so it's like 60 or 65 centimeters across, which is also huge.
Yeah.
Like think of your handheld digital camera and the sensor that's in your handheld digital camera, and then compare that to, more than half a meter. It is really difficult to describe how substantial this camera is, how big it is.
If you could actually view the images that this thing is taking at max resolution on some giant high definition screens or something, how many of these would it take to actually show a full image?
If you wanted to display every single pixel using high definition screens, you would need 400 high definition screens, which would really go a long way in starting to cover the side of a building.
I love it when I just get to scroll through these giant images and see all the cool details. And as you said, like 20 terabytes of data every single night. What is the plan for managing this data and access for it so that people can get into it?
Yeah, so Rubin Observatory is not just a telescope. It is a whole data management system with a community of scientists who have been working for years and years to get ready for this data that is coming. So Rubin Observatory is the telescope, it's the summit facility, but it's also all of the data infrastructure that also had to be put into place to be able to get this data off of the camera, off of the mountain in Chile, and to our supercomputing centers. So the first place it goes is down high-speed fiber optic cables under the Pacific Ocean to the SLAC National Accelerator Laboratory in California. And there we have what's called the US Data Facility, which is a big supercomputing center and is also our primary data processing center. They process a little more than a quarter of all of the data that comes off of Rubin Observatory. They are the first kind of stop in the data processing pipeline. And SLAC is also where this nightly processing takes place. So every time an image comes off the camera at Rubin, within 7 seconds, it arrives at the US Data Facility in California. Then within the next couple of minutes, it gets processed. So we were talking about how you compare these images from previous nights to the current image to find changes in the night sky. That is what happens during those next couple minutes. It scans all of these 3,200 megapixels and it's like, oh, there's a change. And it, packages these identified changes up and sends them out to the world as what are called alerts. And so these alerts are just literally going to be streaming from Rubin Observatory over the next 10 years. But that is what happens during those first couple of minutes at SLAC is identifying all of those changes and sending them out to the world. Then it gets stored. And another set of processing that happens over the next 24 to 80 hours, where now that you have identified these changes, now you can start trying to identify what those changes are. So one of the things that will happen is the solar system identification. So which of these changes are actually objects that are moving from place to place on the sky, but they are the same object. They are just, moving between different spots on the sky. And so that processing starts to happen after that initial 2 minutes. And we also send a copy to the France data facility. They are going to keep the copy of the raw data in France. And then there is also a data facility in the United Kingdom that will, in between those three, those are what are the data facilities that are going to do a lot of the kind of big processing of all the images. We're going to have these annual data releases, and that is going to require a lot more computational power. That's like when you really crunch the numbers and combine all the data that you took over the last year to squeeze the most amount of science out of it. That takes a lot of computation power. And so between those three data facilities, that's where that work is going to happen. Data are proprietary for 2 years to allow Rubin scientists and scientists who have access to Rubin data to be able to do their work. But then after those 2 years, after that proprietary period, the data becomes public, and anyone can use it.
We've spoken with people on the past who were developing some of the systems that were going to be helping track objects in our solar system. And even in just the first 10 hours, this thing found over 2,100 asteroids, which is huge when it comes to planetary defense. There are a lot of things out there lurking in the dark. And I don't want to panic people because we've found the majority of ones that are big enough to, cause a Chicxulub style destroy all life on Earth situation. But there are plenty of things out there that come in and destroy a city or, for example, something like Tunguska or Chelyabinsk, right? How do you envision this thing changing the game for planetary defense?
Oh, it's completely going to change the game. Like Rubin is going to find probably the majority of those kind of potentially threatening asteroids, the potentially hazardous ones. It's going to find most of the ones that would do any sort of damage. I really come back to the saying, like, knowledge is power. Like, we can't do anything if we don't know what's out there. But if we know what's out there, then we can start to formulate some sort of plan if we do find something that does pose a threat. And so, I mean, really the name of the game is just making sure we know everything that's out there that could maybe pose a threat at some point in the future, because then we have as much time as possible to be able to do something about it. Rubin is really going to fill in that gap in the southern hemisphere sky and help us know even more what's out there.
And then we combine that with all of the amateur astronomers. I call them amateur astronomers as if they aren't completely professional in their ability to hunt for these asteroids. And then things like NEO Surveyor that we're hoping to launch into space. If we combine all of this together, that's going to give us the knowledge that we need because, it's just a numbers game. It's a matter of time before something comes in. And with all of our innovations and things like DART, and hopefully with our observations of the upcoming asteroid Apophis, between all these things together, hopefully we can literally save the world. But, you got to start with having the information. But something that I'm really interested in, because we've only detected like 2 of these things, are interstellar asteroids. We've only found, Oumuamua and Borisov, and that was really difficult. But with this kind of data, do you envision that we'll be able to spot a lot more of these objects that are coming in from outside of our solar system?
Yeah, I mean, if they are passing through our solar system and are there to be found, Rubin is our best chance at finding them. We've only found 2 so far, so it's really hard to make, conclusive predictions with only 2 objects. But people have tried because that is definitely something that we're very interested in. Interstellar objects are a really interesting way to be able to study other planetary systems directly. We can study their composition as they pass by, and compare that to what we see in our own solar system and gain more knowledge about how planetary systems form and what they form from. And so these are like really interesting and valuable objects. So the only way we have to study other planetary systems directly. However, we are kind of at the whim of whenever they pass by. We can't really choose when one might pass us by, But if they're passing through our solar system and exists to be found, Rubin is our best chance to find them. And I think that the current estimates are we'll find somewhere around 10 interstellar objects over the next 10 years, about 1 a year. But again, it's really hard to make like really conclusive predictions because we've only found 2 so far.
We've also spoken recently with Brown and Batygin, the team behind the search for Planet 9. And that's a really challenging thing, given that this object, if it does exist, is so far away from the sun. So we're dealing with low light conditions and an orbit on the scale of thousands, if not tens of thousands of years. Even if we're seeing the night sky over the course of 10 years, it might not move that much on the sky. Is it possible that this could help us find where it is, if it exists?
Totally. Yeah. I know you always have to caveat with if it exists. But again, if it exists, I think Rubin is our best chance at finding it. The Planet 9 hypothesis comes from this set of objects. There's multiple aspects to it, but the initial proposal was really inspired by this set of objects that were clustered. Their orbits were clustered in a very peculiar way that you couldn't explain unless something was essentially shepherding them into that configuration. But there's been a bit of a debate over the last 9 or so years on whether that is a real effect or whether that is due to the way that we observe the solar system from here on Earth. And so Rubin is really, I think, going to break I don't know if I want to call it a tie, but it's going to, I think, be decisive one way or the other. So either it's going to find more of these objects that support the Planet 9 hypothesis, or it's going to find objects that refute it so that, we no longer need a Planet 9 to explain what we're seeing. Or the third option is we find Planet 9 directly. So those are kind of the three outcomes that I see. But I think regardless of those three outcomes, we will answer the question of whether Planet 9 exists.
Well, I'm hoping that we can answer some of these big questions, and we need a telescope of this scale in order to help us do this, which is why I'm so excited that there are so many of these larger scale telescopes coming online. But I tell you, I was sitting there staring at some of these images, just absolutely slack-jawed at their scale and detail. And I know this is an audio conversation, but I want to give people some idea of what these images were like. So let's start with that image of the Virgo cluster. What were we seeing in that field, and what really stands out to you scientifically?
Yeah, so Messier 49 is the largest elliptical galaxy in the Virgo cluster. So one of Rubin's first images is centered on the southern region of the Virgo cluster, which is the nearest galaxy cluster to Earth. And what really stood out to me is just how full the images are. Like, you are hard pressed to find empty black space in that image. There are so many galaxies and so many things to see. There are 10 million galaxies in this image. And so anywhere you zoom in and you look, it's just peppered with distant galaxies and small, faint smudges of galaxies. It's just full. And that is really the story of Rubin, and what it's going to do. It's just going to fill out what we know about the entire southern hemisphere sky. The whole southern hemisphere sky is going to look like that after Rubin. So I think for me, again, I'm really biased toward solar system astronomy. That is my science area of expertise. It's what I love. But just I was not prepared for the sheer number of galaxies, like the faint, tiny little smudges that you see when you zoom in. I was not prepared for how many of those there would be.
Yeah, it was like a reflection of that moment of the first time I saw my first deep field as a kid. And the first time someone explained that to me, just even as a child, feeling this deep upwelling of emotion, of this understanding of just like how tiny we are in the scale of the universe and how special it is that we get to be here and look out at all of that. It just fills me with this absolute awe and this gratitude that we get to be here to see all of this after all this time of humanity trying to understand the universe. It is just unbelievable what we're going to learn.
Yeah. As Carl Sagan said, we are the universe trying to understand itself. And I think there is something so beautifully poetic about that. And I'm reminded of that every time I pull up our images, any images from a space telescope, really, but our images to just the sheer number of galaxies. Every one of those galaxies has billions of stars. And so it's really special to be here at a time when we can do this sort of thing.
And that other image of the Trifid and the Lagoon Nebula, it by itself is a stacking of like 678 separate images. How are these stacked and processed together? People do this on a lot of smaller scale telescopes, but this is like a lot of data.
Mm-hmm. Yeah. Processing images of that scale really does push whatever system you're trying to do that on, because these images are so huge. You can actually go download the full resolution version of these images from our website. We're talking tens of gigabytes, though. So I don't know if you'll be able to open it with any program on your computer, but you can download it and have it if you'd like. But it was an enormous weeks-long effort to produce just these two images. And one of them, the M49 Virgo cluster image, was actually produced with our scientific processing pipelines that were tuned in such a way to make this really aesthetic, beautiful image of this region of sky. You don't usually need to put that sort of effort into an image that you're only using for science. But if you really want it to be really beautiful, there's a lot of extra fine tuning that needs to happen in order to accomplish that. And it was just an absolutely heroic effort by dozens of people to make these 2 images for the world. I am in awe of the people who made these happen.
We'll be right back with the rest of my interview with Stephanie Deppe after the short break.
Greetings, planetary defenders. Bill Nye here. At the Planetary Society, we work to prevent the Earth from getting hit with an asteroid or comet. Such an impact would have devastating effects, but we can keep it from happening.
The Planetary Society supports near-Earth object research through our Shoemaker NEO Grants. These grants provide funding for astronomers around the world to upgrade their observational facilities. Right now, there are astronomers out there finding, tracking, and characterizing potentially dangerous asteroids. Our grant winners really make a difference by providing lots of observations of the asteroid so we can figure out if it's going to hit Earth.
Asteroids big enough to destroy entire cities still go completely undetected, which is why the work that these astronomers are doing is so critical. Your support could directly prevent us from getting hit with an asteroid. Right now, your gift in support of our grant program will be matched dollar for dollar up to $25,000.
Go to planetary.org/NEO, N-E-O, to make your gift today.
With your support, working together, we can save the world. Thank you.
You don't necessarily have to download the whole thing in order to interact with it. Thankfully, one of the tools that came out with this release was a sky viewer that can help people actually comb through this. How can, people who just want to look through it, but also people who are trying to share space with people, use these tools to dive into these images?
From the very start, we knew that Rubin images were going to be giant and really unwieldy and difficult to work with for a regular laptop like that. The whole way that the Rubin Observatory science community, the data processing, everything is designed around the fact that you won't have to download these giant data sets. And that's true for the images too. The images are giant and huge, both in terms of like number of pixels and in just this sheer data volume. So Sky Viewer is our tool where you can interact with Rubin images without having to download anything. You can download your view if you would like. If there's a particularly beautiful area of sky and you're like, I want this as my new desktop wallpaper or my phone background, anything like that, we have a really easy built-in way to download your current view. But the point is to make these giant images available at full resolution without you having to download them. This is our way for you to be able to work or explore or experience these huge images without totally crashing your computer when you try to open it.
I've also spoken in the past with some of the people on the Chandra team who decided they were going to sonify some of their images to help them be shared with the world. There are a lot of people who might not be able to see these images or want a new way to interact with them. How do you see these visual and audio tools helping people connect with these Rubin images?
One of the things we really wanted to do for these first images was also have a way to interact with them, not with sight. Like that was really important to us. And the way we went about designing the experience, so Sky Viewer also has a sonification version of it. We call it Sky Synth. And this is that Virgo cluster image, but conveyed via sound. It's also conveyed via images for those who are sighted, who want to interact with it. But we really wanted to recreate the experience of being faced with this huge image of the Virgo cluster and just exploring, like just almost losing yourself in it. There are so many places where you can zoom in and pan and like find something new. And no two people are going to have the same experience exploring these images. And we wanted to recreate that for the sonification as well. We really wanted to create an experience where no two listeners would have the same experience, because that is visually also, in the visual version of these images, what you're getting. So the sonification piece of Sky Viewer is essentially a random walk. So it kind of sticks you start in one area of the image. And there are 2 layers of sound that happen. The first is we have a central focus area where the average color and average brightness within that focus area sets the pitch and the volume of kind of an underlying hum almost. It's like a continuous tone. And then the central focus area kind of goes on a random walk around the image. It just kind of drifts around the image, similar to like if you were a sighted person interacting and you were just kind of free form exploring. The sonification goes on this random walk. As stars and galaxies enter the central focus area, they play as distinct notes. So galaxies will sound like harps and stars sound like chimes. And so as galaxies and stars enter this focus area, you'll hear harps and chimes sounding. Those are also like redder notes correspond to lower pitch for those as well. So you have this like really multi-layered soundscape happening. My favorite thing to do is to leave it open in a tab in the background and like just let it play as background music because it's really relaxing, I find. But yeah, you have these kind of two layers, this underlying ambient tone, and then the individual notes from the stars and galaxies as they come into view.
Are there going to be opportunities for, community or citizen scientists to get involved with this data?
Absolutely. That is a huge effort that specifically the Rubin Education and Public Outreach team has been preparing for. So one of the things that our team has been working on is setting up all of the infrastructure needed for our scientists to very easily set up citizen science projects. So one of the complications with Rubin data is it's so huge that you can't just download this data and then upload it to whatever your citizen science project platform of choice is. We've partnered with the Zooniverse to do citizen science. But again, the fundamental issue was Rubin produces so much data that you can't download it and then upload it to, for example, the Zooniverse. So what our team has done is cut out that download step. So our scientists who want to create a citizen science project just say, I want this data to go to Zooniverse, and then it just happens and you can set up these Zooniverse projects. And so we actually have a couple that are coming out very soon. Actually, by the time this show airs, we might already be out and done because we expect a lot of attention on this first project for sure. So sorry if you missed the first one, but there's going to be lots more citizen science projects, including additional data for this one that maybe you missed.
I love Zooniverse projects. I'm definitely one of those people that spends my extra time just clicking through Zooniverse projects.
Yes, we will have a lot of citizen science projects on Zooniverse, I think. There's going to be a lot of data that you just need human eyes and that kind of volunteer effort to be able to sort through all that data and really get the science that you need. There's just some things that computers can't do, and you need humans for it. So citizen science is going to be a huge part of science with Rubin.
So what comes next for this telescope after the commissioning phase is done? What last steps do we have to do before it goes into full science operations?
Yeah, so right now, the observatory is in what's called science verification. And so we are kind of closing out this, it's a bit of a blurry line between commissioning and science verification, but we are now transitioning from we've turned everything on and now we're making sure it works together to, now we're making sure it works well. And so that is the phase I think we're in now, is that verification phase that here are the data sets we have identified to verify that from a science perspective, the observatory is working as well as it should. And then we're looking at kind of end of 2025 is when this big 10-year survey is going to start. So it's coming very, very soon.
And how are you going to be collaborating with other observatories? Because I know already the people at the Large Magellan Telescope are ready to kick into high gear.
Oh, yeah. Yeah. Well, the power of Rubin is really its ability to see everything in detail and repeatedly. And so Rubin is really a discovery machine. It's going to make a whole lot of discoveries that people are going to want to follow up. And we will get some of that follow up from Rubin just because of the nature of the survey. It's going to be back at that same place in the sky, 3 nights later. But the real power of Rubin and the way that it's going to really powerfully work with a lot of other observatories is by providing those initial discoveries, those alerts, those hey, we've never seen this before. And then providing that information so that other telescopes around the world can go follow that up for more information or more data or different kinds of data. Like Rubin Observatory is an optical imaging observatory. So if you want more data about kind of the different wavelengths of light, like with spectroscopy, that's going to have to come from a different telescope because Rubin is only imaging. It has an imaging camera. Or if you want information in different wavelengths, that'll be a different telescope too. But in order to study something in detail, you have to first know that it exists. And so that's what Rubin is going to do is tell the world, hey, here's what exists. Now go follow it up.
Well, this observatory is named for Vera Rubin, who helped uncover dark matter. And we're going to be talking more about her life and her legacy in our upcoming segment. But what do you think she would make of this moment in history and this beautiful observatory that is her namesake?
I like to think that she'd be proud of us, the way that we've designed the observatory, the way that we have very intentionally made choices to, bring in more scientists who maybe have not had access to this type of astronomical data before. We have a lot of folks who are, at smaller institutions who this is going to be game changing for a lot of them because we are the ones who are hosting the data. Like we are taking the data. All you need is an internet connection, a browser, and curiosity, and you can tap in and use this data for your own science. And so the way that we have designed the whole observatory is really about opening access to the incredible science that is going to come out of this. And I like to think that she'd be proud of us for where we've gotten.
And hopefully we can learn more about the secrets of dark matter and dark energy just as much as all the awesome planetary science we're about to do. I mean, my gosh.
Yeah, I mean, the initial name of Rubin Observatory, when it was very, very first proposed, like just a sketch on a piece of paper, was the Dark Matter Telescope. So it's very fitting and very full circle that our namesake provided the first convincing evidence for dark matter. It's all full circle.
Really. Well, thanks for joining me, Stephanie, and sharing all of this. And seriously, good luck to you and the entire team as you go forward. You're going to be providing the space community just such a wealth of knowledge, just a beautiful asset that we can use to learn more about our universe for decades to come. And it will take us decades to go through all of this data. So seriously, thank you for everything you guys have all done.
Yeah, I mean, there's a whole generation of people who's really going to grow up with Rubin Observatory. Rubin Observatory is going to be the data set for generations. And I cannot wait to see all of the discoveries that come out of it.
Thank you so much.
Thanks.
While the Vera C. Rubin Observatory represents the future of astronomy, its name honors a scientist whose work fundamentally reshaped our understanding of the universe. Vera Rubin was born in 1928 and passed away in 2016. She found the first convincing evidence of dark matter after it was first suggested by astronomer Fritz Zwicky. But her impact extended far beyond her research. She believed science was for everyone and spent her life working to make that a reality. Rubin didn't just break barriers. She worked to remove them. She challenged hiring committees, called out conference organizers who excluded women, and used her influence to elevate others. She insisted on inclusion, not just as a value, but as a prerequisite for good science. Known for her warmth and humility, she mentored countless students and colleagues, often going out of her way to ensure young scientists, especially women, felt seen, supported, and empowered. She also raised 4 children, all of whom earned PhDs in science and mathematics, which is a powerful reflection of the way that she nurtured both curiosity and resilience. Much of Rubin's groundbreaking work was done at observatories across the American Southwest, including Kitt Peak, Lowell Observatory, and Palomar, where she became the first woman officially allowed to observe. She spent the bulk of her career with the Carnegie Institute for Science, whose support was instrumental to her research. One of Carnegie's earliest sites was Mount Wilson Observatory, which is visible on the mountain over our headquarters in Southern California. Vera fought to get data access for women at the observatory in a time when we were still excluded from using the telescopes directly. Our next guest, Jess Soto, is the STEM Strategies Coordinator at Mount Wilson Observatory, a longtime educator at Griffith Observatory, and the founder of Science Women Shirts. She joined me at Planetary Society HQ to reflect on Vera Rubin's life and the lasting impact of her work. Thanks for joining me in our studio, Jess.
Thanks for having me.
I know you've been on the show before, but you also run a small company. You want to honor the legacy of women in science. And now we, for the first time, have a telescope, an observatory named for a woman in science.
Yes, it's really exciting. Vera Rubin, right?
Mm-hmm.
So what an exciting person to celebrate, because her accomplishment was so relevant to astrophysics and just some revolutionary changes and concepts on how we saw galaxies and the universe and just certain things that were invisible that she brought to light, so to speak.
What were some of the things that Vera Rubin did that led to this discovery, this idea that dark matter was a thing? Because now that's something we just kind of accept in astrophysics as a huge pillar of what we try to research.
Right. So she was really interested to see how galaxies work, right? And especially with spiral galaxies. And contrary to the popular belief that the outskirts of galaxies should be rotating less fast, it turns out that everything is moving sort of at the same speed, which proves that there must be mass. And come to find out, it's dark matter.
It was a time when it was, there were limited opportunities for women to do this kind of research. And she was very discouraged, even early on, from going into this field. What were some of the things that she had to overcome?
Her physics teacher, I believe one of her first physics teachers even told her, good luck. Just as long as you stay away from science, I believe, was something along the lines of how he sent her off when she was excited and told him that she got accepted to Vassar. That was what he reciprocated. And that was a little discouraging. And I think it kind of geared her away from her love for physics. She wanted to apply to Princeton, but Princeton wasn't accepting women. So they also pretty hastily, as she put it, rejected. I'm pretty sure they regret that after.
I hope they do. Really, though, the number of things that she had to face during that time, I've met some women in science who've had some really difficult times, and it made them really thick-skinned and kind of off-puttish, almost confrontational when they're trying to deal with other people.
Absolutely.
But Vera instead took that energy and tried to do what she could to welcome as many people as she could into science.
Yeah.
What did she do for women and underrepresented groups in science during that time?
So from my understanding, even from folks that I know that had the privilege of working with her, she seemed to be kind of wise beyond her years. She definitely fought for women to have an equal opportunity and to be seen as folks that men can collaborate with. I don't know if you heard about the bathroom skirt incident in the skirt. I don't know if I'm phrasing that right, but over at, oh my gosh, what observatory was that? Was that at Palomar?
Oh, I think that's right, actually.
Yeah. Where there was no restroom for women. So she cut out a skirt and not an actual skirt, but, something like a piece of paper or something, and placed it on top of the little man sign on the bathroom and said, there, now you have a women's bathroom. It's one of those things that she was in the thick of during a time when women were starting to really be a part of the science. And it's, as you could see, it was decades of a journey for many women in science, from Katherine Johnson to, back all the way back to the Harvard computers, which were really astronomers. They mapped the entire celestial sky. So it's really crazy to me to see that even in her time, by the 60s, 70s, she was still fighting the good fight, so to speak.
And so many of the women that you just named are women that you've tried to honor through your T-shirt line.
Yeah.
Why is it so important for you to share the stories of these women, so much so that you were willing to take this veer off into a side project and try to represent them on shirts that people can wear?
Yeah, because I think it's exciting when you go into a store and you see certain legends, so to speak, represented, like Einstein. And that's a common one that you see in most gift shops at museums, or Nikola Tesla. But there are so many that we are recognizing now that just were forgotten. And they contributed in ways that were just as important to science as like Tesla and Einstein. Henrietta Leavitt, that I mentioned, discovered the star that ultimately helped us have a cosmic yardstick and led to the discovery of the universe outside of our Milky Way galaxy. Katherine Johnson got us to the moon and back successfully, safely. I mean, these are things that are just overlooked, in my opinion, and all too often forgotten. Cecilia Payne, Annie Jump Cannon, and Vera Rubin is up there with all of them as well, And it's exciting because these are women that I think are just now getting that kind of recognition more than ever. And I'm proud to be a part of that time. So I figured, why not help? Why not let anybody who wants to wear a shirt that mentions their name, help them become a common household name like Einstein.
But despite all that progress, we are in a time where opportunities in science are really shrinking due to budget cuts. But also,
Yes.
and I think Vera Rubin is a very concerning example of this. We're in a time where diversity, equity, and inclusion programs are trying to be removed by the government, and mentions of it on government websites are being removed. And we got reporting from both ProPublica and Space News earlier this year that they were going through the NASA websites about Vera Rubin and removing bits of her history about the way that she mentored women and tried to open up opportunities for them at institutions. In that context, what kind of wisdom do you think we can take from Vera's story? What do you think she would say to us in this moment?
That is a really good question. I would think it doesn't define us. It doesn't truly define us as a people in science right now. I think that a lot of people do not agree with this situation. It's something that we have to keep fighting, unfortunately. And so I think we just need to kind of stand our ground and just continue to really focus on the science and do what we can in order to stand up for women, because it is just one entity and a very powerful entity. We all love and are grateful for NASA, but I think that we live in a different time, and it really actually misrepresents us as who we are. We are inclusive, we have diversity, and that's not something that is really going to change just because they remove the past. What do you think she would say?
She's given some really good speeches and was very passionate about the idea that every person can make a difference.
Right.
And that you need to push past these barriers and just keep striving. I mean, what an inspiring woman. I can only think that, if she could do it in those times, we can lift each other up now.
Exactly. I love that nothing ever geared her away from being who she genuinely is. And her legacy of, being the mother of dark matter is not the only thing that she's really known for in science today. She's known for being all-inclusive, for being fair, for just really being kind to everyone. And that's something that obviously, although it's a personal character, has played into her professional career. So I think that's wonderful.
And now we have this beautiful observatory that's going to be looking at the sky and helping us to unravel the mysteries of the questions, but also give data access to people all around the world who might not have had it otherwise.
Yeah.
It's a perfect namesake.
It's amazing. Yeah, it's really great.
Well, thanks for joining me and for sharing some of her story and for doing what you can to share the stories of these women that have uplifted so much of us in science. I don't think either one of us would be here without them.
That's right. Yeah. Thank you for that. Thank you for helping me get the word out there too, and to remember these incredible women.
Here's to Vera Rubin and all of the people who open the doors for people like me, Jess, and Stephanie. May we honor their legacy with awesome science forever. Strangely, just after I finished speaking with Stephanie Deppe at Rubin Observatory and its potential to detect things like interstellar objects, wouldn't you know it, a new one was discovered. 3I Atlas is the third known object to enter our solar system from interstellar space. This discovery was reported on July 1st, 2025, by the NASA-funded Atlas Survey Telescope. That's the Asteroid Terrestrial Impact Last Alert System, which is also located in Chile. There have been two previously detected interstellar objects you might remember: the mysterious asteroid called 1I Oumuamua, and the more comet-like 2I Borisov. Like Borisov, 3I Atlas appears to have a tail, which is fueling excitement among astronomers that are eager to study its composition. Now let's check in with Dr. Bruce Betts, our chief scientist, for What's Up. Hey, Bruce.
Hey, Sarah.
Now, I swear I did not do this on purpose. But as I was talking to our guest this week about the Vera Rubin telescope, I asked her whether or not it was going to help us find these interstellar objects. And then literally a few days later, here comes the third interstellar object we've ever discovered. Can you tell us a little bit about this object that we found?
Yes, 3I/Atlas, the 3 for the third interstellar object found. So it's come off from elsewhere in the galaxy and comes zipping through it. Anyway, it's big, it's out there, it's not going to hit us, and it's interesting because it comes from elsewhere in the universe, the grand universe, elsewhere in the galaxy, and is flying through our solar system. And you can tell it's coming through because it's got this high-speed hyperbolic orbit speed that you plot it backwards, it leaves the solar system. You plot it forwards, it leaves the solar system. So don't get attached.
Some of my favorite comments online are about the direction it's coming at us from, because it's coming from, Sagittarius, which is kind of where the center of our Milky Way galaxy is from our perspective. So people are making all these stories like it's coming at us from the galactic core.
Just because it's coming from kind of that direction, we're 27,000 light years from the galactic core. So, but maybe, and yes, it is, and it's awesome.
If people want to see this object, is it something they can actually see through their telescopes?
I think it'll be a tough object to see if you don't have a fairly nice advanced amateur telescope. You're going to be beyond, you're certainly not going to see it with just your eyes. You're going to be probably beyond binoculars. If you're in an astronomy organization, astronomy club, you probably can do it. If you aren't, you probably can't, but I'm not totally sure. And there's still, it falls now into the realm of predicting the brightness of comets, which is notoriously like predicting the action of, a drunk cat. A cat should never be drunk. That was just important safety tip.
Well, that's pretty random. What's our random space fact this week?
Random space fair.
That's the drunken cat.
So flying discs, flying saucers. I'm going to talk about these today. But what I'm talking about is what's now called a frisbee or a flying disc. When it was first put forth and started to be a little bit mass marketed, it was originally known not as the frisbee, but as the Pluto platter. Yes, that Pluto. And in fact, it had names of all the planets around the outer edge of the disc, and had a sci-fi flying saucer look to it. And then when the rights were sold to Whammo, they ended up naming it Frisbee because of pie tins and a company named Frisbee, and you can look all that up. But the point is they still marketed it with the Pluto platter initially, and then somewhere in there, they removed the names to get better aerodynamics, and then they just switched the name over to Frisbee. But it had an origin in the land of the solar system naming. My dog loves them wherever they came from. All right, everybody, go out there, look in the night sky, and think about flying discs, frisbees, and Pluto platters, and what you would serve on a Pluto platter. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio. But we'll be back next week to share our show's creator, Matt Kaplan's first zero-G flight. Thanks to Space for Humanity for making the dream finally come true. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review and a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members from all over the world who believe that space is for everyone. You can join us as we celebrate the advancement of space science and the people that make it happen at planetary.org/join. Mark Hilverda and Ray Paletta are our associate producers. Casey Dreyer hosts our monthly Space Policy edition, and now announcing Matt Kaplan as the host of our new monthly book club edition of Planetary Radio. More on that next week. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.